So why don't we start with the diploma question? I took off the multiple choice ending, but this is a question that was on a previous diploma. This is one of those ones that I know I need to prep you for. So here's the concept here. A student is going to use acidified KMNO4, and they've given us the concentration. So this time we actually know the concentration of the KMNO4. And what we're going to do is we're going to titrate samples of Fe2+. Brief side note. Any of you guys have like well water because you live out of town? Do you ever get like test or inspection reports done every once in a while where they like just make sure it's still safe to drink? I've actually heard of a teacher in Pincher Creek. He actually used to do this. He'd get kids to bring in students who aren't using like town water. They'd bring in water and they would test for the iron concentration just to see whether there was like too much or too little, or in terms of other little things there. So I mean, imagine the scenario here is that you want to test to see whether there's any iron in your water supply. Because that's the thing, we do not know its concentration. We do know the KMNO4's concentration. Why do we know its concentration? Well, we either made it ourselves, or we titrated it, right? But either way, we know the KMNO4's concentration. We then have unknown samples of iron. So water has a trace amount of iron in it. We want to calculate its values. Now, they give a little more hint here. They said the iron ion is actually going to go from iron 2 plus to iron 3 plus. And then, just like we've done in the past, I made a nice little chart here, where there's the initial and final readings on the burette. They gave the color changes here, and they asked us to find the concentration of Fe2 plus. I actually believe you guys have the skills right now to solve this even. Okay, so why don't we try this one right now? If you want to maybe just like write down just the basics in the table here on a blank sheet of paper, why don't I start with kind of like the end problem here? So I'll give you a second here. Write down all these values just for your burette. Do you guys remember doing this from last semester? While you're writing it down, then let me remind you of some of the concepts here. What we're looking for is the right color change. I will just tell you how the color change works on this one at first, and then I'll give you the notes on it in a bit. How many trials do you need for it to be considered legitimate? Say it. Yeah? And do you remember what the range is? Say that. No, not 0.8. You need 3 trials within 0.2. Yeah. The way it works is that the margin of error is plus or minus 0.1. So that again, the margin of error is supposed to be plus or minus 0.1, meaning that you can go up a tenth or down a tenth, but that's as far off as you're allowed to be. That's the standard that we're going to base things on. So as you guys are writing this down, you can probably make a guess here that the 3 trials we're looking for are probably going to be trials 3, 4, and 5, because they're the only 3 that actually have a pink color 3 times in a row. I'll explain the color later. And then if you guys remember how that burette tool works, it's not a one measurement tool. I know that sounds kind of strange, but like a scale is a one measurement tool. You take an object, you put it on the scale, you read the number. You're done. A burette, I guarantee you, a burette has to be measured twice. You always have to have an initial reading and a final reading. You guys remember what you do with those 2 numbers? Subtract them. Yeah, it's always about the difference. You can never use a burette with just a single reading. One of the reasons why, if you guys have forgotten how that looks, the burette is that long, thin tube that looks like this, with little markings on the side like this. And then there's like a little stopper you twist. One of the reasons why is that the markings only go from, say, about here to here, but there still is liquid in the bottom of the burette, including that little tip right there, and that stuff is not ever measured. Like, we just don't know how much is from like here down to there. So it always has to be like start to finish and subtract the 2 numbers. You guys have your green sheets nearby here? Let's talk about how this reaction is going to work here. We're going to use acidified KMNO4. So I'm just going to have to draw this from where I'm at. Hopefully you guys can find it in your own spots here. If we're using acidified KMNO4, it means that we have 3 things. First, the acidified means you have H+. which means that right dead center in the middle of the table is an H plus right there at the number 0.00. So hopefully if you can see this, that's where an H plus is. That's the acidified part. You also have KMNO4, which means that you have K plus. K plus is literally like the second lowest thing down at the bottom down here. You can see where that's at. You have K plus. But you also have MnO4. And MnO4 is the third one from the top. You guys find that? It looks like this if you can see from where you're at. This one way up here is the MnO4 minus. H plus is right here, and K plus is in the middle there. Now, normally, MnO4 wouldn't work on its own, which is why it was really important for it to be acidified tin. So you actually do have both the H plus and the MnO4 required. Collectively, these two things right here are your oxidizing agents or reducing agents. Good. You're getting a little faster at being able to recognize that. Right. The reason why is that things on this side of the table are your oxidizing, and these guys down here are your reducing. Like eventually you'll start to, it'll sink in faster. So you need both of them though. They're both the oxidizing agents. If you don't have the H plus, the reaction doesn't work. You guys are actually going to see this in our lab on Monday. I'll probably intentionally do it and forget to include a little splash of acid, and you'll see that the whole thing just does not work properly. So far, by just using the acidified KMNO4, I've now got some oxidizing agents. I need a reducing agent. Well, what we're trying to figure out in this particular example is how much iron there is in, say, your water supply. Iron 2+. So that guy is right about here. You can see it's at positive 77. Just roughly see that from where you're at here. Which means we do now have a spontaneous reaction. Our spontaneous reaction is between the MnO4H+ and the Fe2+. I want to set that aside for a second here and remind you guys how a titration works. In your titration, the math usually looks something like this. You have a volume. You then multiply that volume by a known concentration. Brief aside. I'm going to say this a lot over the next day. How do we know this concentration? Either you made it yourself, or you have already titrated it to calculate its concentration. But you have to know at least somebody's concentration somehow. And the next step is that you need some sort of ratio. And then usually the way that I wrote my last step is I write 1 divided by a liters number. And what ends up happening is really this liters cancels with that one. If this is item A, it cancels this A down here. If this is item B, you're now left with moles per liter of item B. In this diploma example, we're looking for the moles per liter of iron 2+. I'll leave that up there for a second if you want to copy that down. We start with a volume amount. We multiply it by a moles per liter. We have to know at least somebody's concentration, either because we already titrated it or because we made it ourselves. I can't use that beaker anymore. I didn't make it. What happens to solutions over time? Say that louder. Yeah, they usually get more concentrated. Why? Yeah, water evaporates. Or there's actually one more thing that can happen. This didn't really apply in our acids and bases, but that permanganate, there are certain things that sometimes do react with water. And so slowly over time, now that we've talked about how water can be an oxidizing or a reducing agent, sometimes things can actually react with water and decrease its concentration. So anyways, we don't trust that concentration, but this is our basic setup. Take a volume times by a moles per liter. We need a ratio. We need 1 over liters. We actually have many of these numbers from the previous example. I'll go back here. I have a volume. One of my volumes is right here, 25 milliliters. What is it, 25 milliliters of, though? It's the 25 milliliters of iron. So if I'm trying to set this up in my little example right here, since iron is what I want to know about, Do I put the 25 milliliters in this location or this location? Yeah, the last one. Because this is going to be about our MnO4 minus plus our H plus concentration. Those ones are going to go here, and we're going to cancel that with these ones down here. So we need to actually go 0.025 liters as our ending amount. From kind of a practical point of view, do you guys remember what tool we use to measure that 25 milliliters? What it's called? It's called a pipette. Yeah. Pipette is the tool that looks kind of like this. It's a long, thin tube with like a bubble around it like that. And then there's like a little 1 calibration marking on there. That's a pipette. So we're going to put 25 milliliters of our iron solution in there. We're also going to need to know a couple other things. If I go back, we need to know what concentration of the KMnO4. So I do have that concentration, right? 6.31 times 10 to the minus 2 would go here. 6.31 times 10 to the minus 2 is my concentration. I'm just lacking 2 other numbers. One number I'm lacking is how much volume did I use? And then the other thing I'm lacking is my ratio. I'll come back to the ratio in a second, but let's do our volume number next. You guys have all this table written down, right? Anybody subtracted these values yet? Okay, help me out. This one right here, I could probably do in my head. This is going to be 17.25, right? You probably can skip the purple ones, but let's do it anyways. Here, I got a calculator. 1365 minus 1755. On this one, I got. Ooh, that's not right. Ah, that's why. It's 3565. I got 18.10. 2640 minus 1005. I got 1635. 4265 minus, what is that, 26? 2640, 1625. 1685 minus 0.55, 16.3. Zero, really. Does that make sense to everybody, how I subtracted those values? I want to talk about color change later. But if you guys can just go with it, I mean, clearly the only 3 trials that were consistent in both the color change and in the volume amount are these last 3. So I need to average these last 3, but you can probably do that in your head, right? 16, 35, 25, and 30 are just going to average to give you 16, 30 milliliters. That's your average. So this would have been calculated by using the burette drop by drop by drop. Ideally, that's hyper accurate, right? Because you're literally going to the drop. So that number would have gone here, 0.01630. Yeah, 1630. Is this ringing a bell? You guys remember doing this about, I don't know, 3 months ago, 2 months ago? Okay, last thing we're missing though, we need to have a ratio. None of this is good unless we actually know the balanced ratio, which is why I knew I had to spend a lot of time working with you guys on being able to predict balanced equations. So going back to this thing right here, can we write ourselves a balanced redox equation? Well, here's the steps again. Write out one equation going forward. So I'm going to write out the MnO4 minus plus 8 H pluses plus, this one's odd, it's 5 electrons. That's going to turn into Mn2 plus and 4 waters. That is our reduction equation. What's happening in our oxidation equation? Iron 2 plus. There's some iron in your well water. We want to test and see how much of there is, right? Common mistake. Don't write what I'm about to write here. But some people would say, hey, this is going to turn into iron solid. But that doesn't work because then you'd have to have 2 electrons on this side and they'd both be reduction. So that's incorrect. It actually gave you a hint in that diploma example. It actually goes to iron 3 plus, goes backwards and spits out 1 electron. we don't actually need to write the whole thing. Because what were we really missing in our Stoic equation? We just needed to know the ratio. So I really don't need to write out everything. I just need to figure out what the ratio is. There's 5 electrons to 1 electron, right? So all you need to do is times this whole bit by 5 right here. And I mean, I could sum this all up and write up a new equation, or what I really need to know is what was I working with? One of the things that I want to know about is iron 2+. And then the other thing I wanted to know about is either potassium or permanganate. And because it's potassium permanganate, let's focus on this guy right here. My ratio is you need 1 permanganate for every 5 irons. Okay, that's all I really need this for. I don't really need to write out all of the equation. I just need the basics of it. So now if I go back to here, I know I need 5 irons for every 1 permanganate. I wasn't sure at the time which of these two things I would use, whether I would use the permanganate or the H+. But because the concentration I was given was of the permanganate amount right here, then that's the one I went with. I want to make sure I'm clear as to why I was allowed to do this. Do you guys remember from our first unit the idea of if I have KMnO4 in an aqueous format, how it's allowed to dissociate into K plus and MnO4 minus? Do you guys recall that a little bit? If this guy had a concentration of 2, then both of these would have a concentration of 2 because there's a nice 1:1:1 ratio. Hypothetically, this could come up. If I gave you CaOH2 and it turned into Ca2 plus and 2 OH minuses, if this had a concentration of 2, this would have a concentration of 2, but this guy would have a concentration of 4. Do you guys recall this? So that's why this is allowed to work, though. I was given a concentration of KMnO4, which, because there's a nice 1:1 ratio for both of these things here, means I either have the concentration of K, if I care about it, or I have the concentration of MnO4. And isn't MnO4 what we want in our example? Long story short, then, the ratio is then 5:1. So there, I have all I need now. This times by 5/1 divided by this gives me our concentration. Do you guys recall this to some degree? I promise you're getting a titration question. Like it's a guarantee. It's one of the outcomes that, like, there's not a lot of ways of asking it. It usually is in the format that I just showed you. If it's multiple choice, it's kind of nice because at least if it's multiple choice, if you get one of the 4 answers, you probably did it right. Whereas if it's numeric response, it kind of sucks because you might never catch your mistake. Right? But they'll usually give you a nice little grid that looks like this. You have to do the addition subtraction. You have to write yourself an equation and piece it all together. Rebecca. Oh, good call. Yeah, I didn't actually finish that, did I? This would give you 3 sig digs. That would give you 3. This right here technically would give you 4 all the way through. So I guess, yeah, 3 is your limiting then. Yeah, if you guys recall, the rules for subtracting here means you keep your precision, right? So this one right here, when I use my calculator, it actually spit out 18.1, but it's actually 18.10. Yeah. Often on measuring devices, and this is a good example of one, when you're actually measuring in the lab, and like here's the marking, if the meniscus comes to right there, then you go with a 0.5. If the meniscus comes to right here, you go with a 0.0. Never go with 0.4 or 0.3 or 0.2 because you don't really know that. So you can either give it a halfway point or you can give it on the dot and add a 0 to it. But like keep that precision the whole way through. Don't lose precision just because you subtract numbers. So let me talk a bit about colors now because I've been skipping that. How do you know when a titration is finished? Well, in acid-base titrations, there's a color change. Because what do we throw into an acid-base titration to make it change colors? Indicators. Yeah. But that only works if you're going to have acids and bases neutralizing each other. What happens in this case where you have iron reacting with permanganate? Was this an acid and base equation? No. What would happen if I threw phenolphthalein in? Jack squat. Nothing would happen, right? So that's one of the issues with trying to do redox titrations is that how are you going to know when to stop? There's no obvious color change. Well, that's why it's actually quite helpful that there are two chemicals known that are relatively strong oxidizing agents. And the two chemicals, one I've already mentioned, is permanganate. Permanganate comes in a purple format, but as you reduce it, it reduces to a clear color, and there's actually a color change noticeable. When this solution right here gets reacted, it actually goes into a clear form. Now, if we actually play around with this carefully, I can actually make it, rather than go from here to here, I can actually kind of make it turn colorless to purple. I'll show you how in the lab, but there is a color change available. And there's also one more that changes color, dichromate. When it goes from dichromate into just a chromate ion, it goes from orange to green. That one's not quite as nice. And the reason why is that there's that iffy territory in the middle, where it's like, well, now it's orange, now it's brown, now it's green, or like some in-between color. How do you know when it's distinct? Well, that's why permanganate's awesome. There's really two reasons. I think this is even one of your lab questions. Why do we use permanganate? One, it is a super, super high oxidizing agent. Really, there are only a few things that permanganate will not cause to oxidize. Permanganate is like literally the third guy on the list. So unless you're trying to oxidize fluorine or water and lead sulfate, like it will react spontaneously. But the other reason why we like it is that it also changes color. What happens when, like, say, I don't know, pick the next one on the list here. What happens when gold aqueous turns into gold solid? It's not really as noticeable of a color change, perhaps. I mean, you're going to make it precipitate, but it's not really got like a nice distinct color change. So the other one is actually, let's see, 1, 2, 3, 4, 5, 6, 7. It's the eighth one on the list. The dichromate, which is at positive 123, turning into chromate, it also has a color change. So either of these are useful because as the reaction progresses, you can actually see colors changing. That makes sense. So here's how we usually set up ours then. What we're going to do is in our tube, what we're going to do is we're going to put an unknown down here. For example, in the one we just did, this would be iron 2+. We'll put our iron 2+ sitting down here. It will be clear. Then in our tube, we're going to put the potassium permanganate. The potassium is really not relevant. It's the permanganate that's really important, and it is purple. P-U-R-P-L. When I add the potassium permanganate to the iron, what's going to happen? Trick question. Nothing will happen. Why? Because it's not what? Yeah. So here's what we're going to do. We're also going to add a few drops of acid. Remember how in previous titrations you had to add a few drops of phenolphthalein? Well, if this does not also have some H+ ions nearby, the whole thing doesn't happen. Okay. So now that I've gotten the trick out of the way, what happens when you add this purple solution to the stuff down here? Well, what ends up happening is your purple stuff turns colorless. And so as you add your drops of purple in, it should be purple, and then instantly it's going to start turning clear. Kind of like normal titrations do. But what's going to happen is eventually you had some irons in here, and you had some irons in here. Eventually, well, this one gets used up, and this one gets used up. And now there's no more iron left. What happens when you add one extra drop of the purple stuff? It will then stay purple, and that's our endpoint. So really, it operates the exact same way as the acid-base titration does, but on a completely different mechanism. Rather than it changing colors due to indicators, it's changing colors just due to the fact that it just naturally changes colors. We'll always make sure we add an excess amount. Good call. We'll use concentrated acid, because you're right. If we were to run out of the H+, then it wouldn't react properly. So, thing is we're usually using very, very small dilute concentrations of the Fe2+. So like 3 milliliters of like concentrated acid is usually well more than sufficient. Good question though. So again, here's kind of my pictures on this one. You add, and eventually you're looking for just the faintest color. As soon as you have like just the littlest bit of purple left over, that should mean you've reached that endpoint or equivalence point. So, I put this slide on here to kind of remind you of the process by which we're doing things. It's really a stoic process where you need to go like from here to here to here to here, only this isn't like exactly the way it works. It's not going grams to moles to moles to grams. It's more like this. You have liters. You then multiply by a mole per liter to get to moles. You then use your ratio to stay with moles, and then you divide by liters to get to moles per liter. That's kind of the basic process. It's always the same setup, though. It's always liters, moles per liter, ratio, divide by liters. That's kind of the basic concept. You guys have done enough titrations. So why don't we try 2 more examples? And I think this really gets solidified, though, when you actually do the titration, hence the doing the lab on Monday and Tuesday. So here's an example. I've got a solution of potassium permanganate solution, and we are going to try to oxidize some chromium 2 ions to chromium 3. Very, very similar. You've got some well water, and you want to see, is there chromium in my water? So we're going to add some potassium permanganate to this. We want to know the concentration of the chromium ions based on our analysis. This is honestly the exact same question we just did, only rather than it involving iron, it now involves chromium. But it's like the same thing. So, first thing I'm going to do, I'm going to subtract all these values. So 14.2 minus 2.7 gives me 11.5. 11.2. 11.1. And 11.1. Step 1. What did I just calculate? Well, I calculated the volume of potassium permanganate. So if I average the 3 I'm allowed to average, which is these 3 right here, 11.1, second 11.1, and 11.2. So my volume is going to be 11.13 repeating milliliters. That's one of my volumes. I have a second volume right here, which is 25.0 milliliters. 9 times out of 10, if a student makes a mistake on this, they get the 2 volumes in the wrong spot. So I'm going to make sure right here that I'm very clear as to which one is which. The 11.13 is of my MnO4. And my 25 milliliters is of my chromium 2+. Just make sure you're super clear as to which volume is which, because you don't want to mess that part up. If I can kind of go down below, I'm going to set up my basic concept now. I need a volume amount multiplied by a moles per liter amount, multiplied by a ratio, and then really you're dividing by a final volume. Always the same sort of setup. And then just work backwards. What am I looking for? What's the whole goal of this whole exercise? What am I trying to calculate? The concentration of chromium. So because of that, I'm going to throw my chromium 2+ sitting right here, which means that this bottom number here better be my permanganate number, which means my starting amounts better be my permanganates, my ending amounts better be my chromiums. I'm just going to start throwing numbers in the right spots. The concentration, what was it? 0.0144. And then my permanganate amount was in the table, so that was... oh, by the way, can I show you guys a little trick? Rather than dividing into liters every single time, if you want to make this number in milliliters and this number in milliliters, it'll actually be consistent. I don't want breakfast. Yeah, go ahead. Well, if this one's in milliliters, as long as this one and this one are in milliliters, rather than imagining that this liters cancels that one right there, why don't you just pretend that this milliliters cancels that one there? So if you really wanted to, you could make this 25 milliliters, and this one could be 11.13 repeating milliliters. You know, if you wanted to, you just have to make sure you're consistent. Both of these numbers better be in milliliters then. That's all. Have I done a good job of making it clear as to which one of these volumes has to go where? No. The only thing we're missing then is our ratio. which just means we need to make a quick equation. You don't even need to write the whole equation out. You just need to know what the ratio is. So, I mean, honestly, once you get faster at this, you're going to know that the MnO4 equation needed 8 plus 5 electrons to form Mn2 plus and, what was it, 4 waters? And then the other equation is exactly what we did before. It's just chromium, not iron. So chromium 2 plus is going to go to an electron plus chromium 3 plus. I'm not even sure you need to write this out. Like, if you can do this in your head, the ratio is going to be 5 chromiums for every 1 permanganate. There we go. That's all you need. Once you get more familiar with this, titration questions are actually the gimmies. They should be. Because, like, it's very standard, very traditional. Just do this, do this, do this, do this, right? It takes a while to set up. So, okay, take that number times by 0.0114 times by 5 and divide by 25. I got this, 0.025384. And that was of my chromium 2 plus. Anybody else get that? Awesome. And then just do proper sig digs. I'm assuming it's 3. It's almost always 3. That makes sense? I have one last example for us, and then I can call it a day. Does everybody have what they need from here? No, I'll wait a second. Sometimes from a lab point of view, however, you have to do a double titration. Do you guys remember the term standardizing? To standardize something means to find out its concentration. Here's what we're going to do in our lab. In our lab, I'm going to just write this on the board here. I'm going to get some hydrogen peroxide. I'm just going to buy this just from the store-bought. And if you guys have seen a bottle of hydrogen peroxide, it's usually labeled as being 3% weight over volume. Okay. What we're going to do in our lab is we're going to test and see whether it actually is 3% weight over volume, which means ultimately our goal is going to be to end up with a moles per liter of H2O2. And if you guys can see your data books here, your sheet there, H2O2, hydrogen peroxide, is on the table right below iron. Actually, it's literally the one right below iron 2 plus. It's at positive 0.70. You see that there? So there is a nice reaction that we can take between H2O2 and the permanganate. Right? Basically, in your book right here, it's going to have your MnO4 minus with your hydrogens. Your H2O2 is right here. There you go. You've got your nice balanced reaction. Super easy to do. Here's our problem, however. When you buy permanganate, most of the time you actually buy it as a solution. It is possible to make it from crystals, but most of the time you actually get what I have right here, which means there's a huge fault in our plan. You know how you need to have 3 numbers? You need to have 2 volumes and a concentration. Well, the 2 volumes are easy to measure. We have measuring tools that get you volumes, but the concentration, we have to trust its accuracy. I have a solution right there that says on the bottle 0.00 something, but do you trust its accuracy? No, we can't anymore. So what we have to do is a double titration. What we have to do is do a titration to calculate the concentration of the permanganate, and then from the permanganate, then use that to calculate the concentration of our peroxide. Now, here's the good news for you guys. You're not going to do this on the diploma. It's not an expectation that you should do a double titration. But in a lab setting, this is very common. This is actually the one that Raj told me about, where he was like, oh, I did this one before. So that's what we're going to do in our lab. Basically means you have double the work. It's not harder. It just means you have to do things twice. Fair enough? So let me walk you through the math behind how you're going to do one of these, and then we'll try it for real on Monday. But let me make sure it's clear here. You will not have to do this on the diploma. You'll have to do half of it. You'll either have to do one titration or the other. And hopefully you guys can see this, because when you go to the next page right here, see how there's 2 different tables? One of the tables is for when you calculate the concentration of the permanganate, And then the second table is when you use the permanganate to calculate something further. Okay, so let's try to keep this organized here. We're going to actually use the exact same compound in our lab. We're going to use this one right here. It's iron, ammonium sulfate heptahydrate. Crazy, crazy, crazy chemical. Here's one of the reasons why we like it, though. This chemical right here can be prepared from scratch, and we can trust its accuracy. And one of the reasons why we actually prefer it is actually the reason why you don't like it. You're probably not liking how massive it is to have all these different things on there. But the larger it is, the more likely we are to be accurate on its molar mass, and then for to be accurate on its mass itself. So rather than just using iron itself, by using this really crazy like double salt, you guys remember the term double salt from a previous one? Well, what this is a double salt is, you've got some irons that go with the ammoniums, and you have other irons that go with the sulfates. So anyways, the first thing we're going to want to do is we're going to find this thing's molar mass. So it's going to take you guys a few seconds here. You need iron at, 5585. You need nitrogen at 1401 times by 2. You're going to need a sulfur at 3207, and you're going to want 2 of those. Hydrogen is 101, and you're going to want 8 plus 12, so that's 20. And oxygen, what is that? That's 8 and 6, 14. So I need you guys to calculate me a molar mass of this beast of a chemical here. Does that make sense what I'm asking for you guys to do? Iron is 5585, right? I feel a little rusty here. Right, 5585 plus 1401 times 2 plus 3207 times 2 plus 16 is 8, 6 is, 14. And then hydrogen 101 times 8 there plus 12, yeah, that's 20. I got this. 392.21. Why do I need that molar mass? Why do we need that molar mass? Yeah, we have to make a solution ourselves from scratch that we trust. There's a solution there. It's got a number written on it, but if we want to do it properly, we have to make one ourselves. By the way, whenever I mark you guys' labs, this information down here is often something that you forget to write down. The mass you use and the volume of flask you have. Remember I was marking some labs a while ago. We used like 4 grams of potassium hydroxide in 100 milliliters. Always don't forget that, because really this number, and this number are your starting point. It's going to look something like this. 1.87 grams multiplied by, really you're dividing by the molar mass of 392.21. And then when you divide that by 100 milliliters, you get this. Is everybody able to calculate that value that I threw up on the screen there? I want to talk about that in a second, but yeah, that's what I wrote there, Fe2 plus solution. This is known as your primary standard. You have to have a solution that you yourself made from scratch and that you are highly confident in its accuracy. There are 3 numbers that we put together. 1.87 grams. How are you going to get that number in a lab setting? You're going to put it on a Yeah, scale. As long as we don't have any reason not to trust our scale, we should be confident in that value. The next number is the molar mass. This is actually the reason why we are using this crazy chemical, is because it has a high molar mass. The larger the number, the less inaccuracy you have. I can explain that concept more later. We talked about this in physics a little bit once before. The bigger the number, sometimes the better they are. How do I phrase this better? Imagine that I was giving you a single digit number, like say 5, and I knew you were going to be off by a little bit. If you were off by, I don't know, like a whole digit, imagine you were off by 1 out of 5. 1 out of 5 is 20% off. Does that make sense? So like, let's say it was supposed to be 5, but you actually got 6. You're off by 1. 1 divided by 5 would be 20% error. Does that make sense? But what happens if the number was supposed to be 342 and you were off by 1? What is 1 out of 342? Well, it's not even 1%. Does that make sense? So the bigger the numbers generally means like the less inaccuracy you're going to have when you're off by a certain amount, because the amount you're off by is a smaller percentage. Can I say that one more time? Imagine that you're aiming for the number 5, but you accidentally get 6. So you're off by 1 unit. Right? The percent difference would be like 5 minus 6 would be 1, and then 1 divided by 5 would be 5. 1 over 5 is 20%, right? So if you're off by 1 whole unit when it's out of 5, you have a 20% difference. That's huge, right? 20% off is a huge difference. But what if the number you were aiming for wasn't 5? What if it was 392? What if you got 393 rather than 392? In both cases, I was off by 1 unit. Does that make sense? But 1 out of 5 is way worse than 1 out of 400. Right? So that is the reason why we are using such a large number here, is because this hopefully helps this accuracy. If we're off by a little bit, it won't make as much difference. Wait, the last number right here, this 100 liters, do you guys remember what sort of measuring device we would be using this 100 milliliters in? Good, it's called the volumetric flask. Yeah. And as long as you don't overshoot the calibration mark, and as long as that flask has been made properly, we should have a high trust in this value, and this value, which means that we now have a concentration that we also trust. I want to point one more thing out here. I just wrote Fe solution. This thing right here, in theory, it should dissociate. It should dissociate into 1 iron, 2 of these, 2 of these, and 6 of these. But here's the thing. Wouldn't the concentration of iron be this because of the fact that when it dissociates, there's 1 iron? Right? If we were asking about this guy's concentration, it would be twice as high. If I was asking about this guy's concentration, it would also be twice as high. But we only actually care about the iron, so it's only a 1. So there. We now finally have our firm starting point to work with. Okay? From here on out, I wouldn't say it's easy, but at least it's the same thing we've always done. Okay? Only we have to do it twice. So I'm going to try to go a little faster here because I think I'm taking too long. What we need to do now is, for our first box right here, we need to do our subtracting. So let me go faster. 12.5 minus 1.2 gives us 11.3. 23.5 minus 12.5 gives me 11.0. 34.5 minus 23.4 gives me 11.1. 45.5 minus 34.5 gives me 11.0. The average would be what? 11 plus 11 plus 11.1 divided by 3. 11.03 repeating milliliters. Pretty good with that part so far? Okay, so in our first reaction, here's what we're going to be doing. We need a liters. We need a moles per liter. We need a ratio. And we need a volume. Let's start at the beginning this time. What do I actually firmly know for sure? Iron, right? Because we made it ourselves. So I should make my starting amount be the iron 2 plus because I made it, which means Fe2 plus goes down here. And here, let me close that door. Now I just need to dig back through all of the information and sift through it. and figure out which values we have. So we know the concentration of iron, right? Didn't I just calculate that back here? It was this value here. Can I just label this as value A, just to make things simple? Is that fair? So this A right here, that's the concentration of our iron solution. So that A value is going to go right here. How much iron did I use? Okay, this is where I got to get the numbers right. Let's read through the table here. This right here, this table was the volume of potassium dichromate. So the volume of potassium dichromate, this is actually a dichromate number, not an iron number. So I'm going to have to dig back on the previous slide and see, here it was. It was 10 milliliters was used of this stuff here. So iron was actually 10 milliliters. So 10 milliliters of iron, concentration we just found. I'll do my ratio last. That must mean that this stuff over here is dichromate. And its volume was the 11.03 repeating number. Only thing I'm missing then is I need to know my ratio, which means that it must be a dichromate to iron ratio. Honestly, once you guys get better at this, you're just going to do what I'm going to explain here. Find iron on your table. We've already done iron before, right? How many electrons does the iron reaction require? 1. Okay, this time we're using dichromate. That's the 6th one down. How many electrons does the dichromate require? Okay, so it's a 1 to 6 ratio. So all we're going to need to do here is say that for every one of these, you're going to need 6 of those. That's all. You could write out the equation, but does that make sense as a way to kind of speed things up? Because I feel like I'm moving way too slow for you here. Iron requires 1 electron to go from 2 to 3. The dichromate requires 6 if you look it up. So there, we're good. So I'm going to do all of this now and calculate a concentration of my dichromate. 10 divided by, what was that number again there? That one there. Divide by 6. Divide by 11.03 repeating. I got this. 0.007202, something like that. If it's okay with you guys, can I call that B, just to make it a little bit easier here? We made an iron solution. Made it ourselves. Very confident in it. We now use that to titrate a dichromate solution. I know that on the beaker right there I have potassium permanganate, but it's effectively the same thing. Now we know the dichromate's solution. Now we can do another titration and go from dichromate to, what are we looking for anyways? Tin. So like if you want kind of a diagram here, it's almost like you have to go from iron 2+ to get to your dichromate, and then go from your dichromate to your tin. You get what I'm saying here? So why couldn't we not go directly from iron to tin, by the way? That's a good question. Why do we bother with this whole intermediary? Why do we need to go from iron to dichromate and dichromate to tin? No color change. There's no color change. How would we know when to stop our titration? We could titrate an iron and tin solution with each other, but we'd never know when to stop. Right? Which is why we have to do an iron dichromate solution so that it goes like green to orange or something. And then you have to do a dichromate 1 to tin, which will also go green to orange. So, anyways, let's do this last one here, and then we call it a quits for the day. Anybody done the math on these ones here? Can you save me time? Sure, let's just go with that. 10.5 milliliters. Okay. We're okay with that? Awesome. Speeding things up then. On this example right now then, we got to do the same thing. It's a liters times a moles per liter times by a ratio times by 1 over liters. I'll work at the back this time. We were looking for the concentration of tin ions, so I'm going to throw the tin 2 plus sitting right here. And tin is going to go with the dichromate like this, because we're looking for tin and we're going to come from dichromate. So Cr2O7 is what we're going to start with here. Do I know dichromate's concentration? Yes, I do. I literally just found that. That is what I decided to call letter B. So we're good there. Do I know how much dichromate I used? Yeah, isn't that what we just calculated right here? This is the dichromate we used. It was 10.5. So make sure you get the numbers in the right spot. The 10.5 milliliters goes here. I need to know how much tin I used in my sample every time. I think that's on the previous page. It said right here that I also used 10 milliliters of tin. Do you guys remember what tool we would be using to measure the 10 milliliters in a lab? What's the tool that we would use to measure 10 milliliters with? It's a pipette. Remember that one? It's where you use a little bulb device. Anyways, that's 10 milliliters right here. The only thing I'm lacking then is my tin to chromium ratio. But honestly, I can do the exact same thing I did before, right? Find your chromium one. Chromium uses 6 electrons. Find your tin. How many electrons is tin going to use? 2. Okay. Here, let me draw this out real quick. Here's your dichromate reaction up here. Your tin reaction is positive 0.15. I don't even need you to write out the whole equation. Just know what the electron ratio is. One of them uses 6. One of them uses 2. What do you have to do to the one that uses 2? Times it by 3. So you have a 3 to 1 ratio. So 3 to 1, and now we're good to go. Just times the rest of this stuff. So times this by 10.5, times by 3 divided by 10. Final answer is 0.0227 with sig digs. Does that make sense? Is I going too slow by the end here? Okay. Let me do a quick summary, and then I'll stop for the day. On the diploma, you do not need to do a double titration. Okay, so that's good news. You do, however, need to for sure know how to do at least a single titration. In our lab, I'm going to make you do a double. And if you go off to University of Chemistry, I hope that one day you come back and tell me, Chris, we did a double titration. I know how to do it. That'll be awesome. So, tomorrow, let's do a work day so you guys can kind of get caught up on any other things you need to get finished. And then we'll do the lab Monday, Tuesday. Does that work? Sweet. Okay, I'm done. Thanks, guys.